Today we are telling you about mass ranges of stars low, intermediate, and high. I invite you to stay till the last second of this video. Stars represent one of the most fascinating components of our universe, serving as cosmic furnaces that transform simple hydrogen into increasingly complex elements through the process of nuclear fusion. The classification of stars based on their mass provides fundamental insights into their structure, evolution, and ultimate fate. Understanding stellar mass ranges helps astronomers predict how stars will behave throughout their lifetimes, from their birth in stellar nurseries to their dramatic deaths. This comprehensive exploration examines the three primary stellar mass categories: low-mass stars, intermediate-mass stars, and high-mass stars, each with distinct characteristics, evolutionary pathways, and final outcomes. The mass of a star serves as the single most important factor determining virtually all of its other properties, including luminosity, temperature, radius, lifetime, and evolutionary path. Astronomers measure stellar mass in terms of solar masses, where one solar mass equals the mass of our Sun, approximately 2 times 10 to the power of 30 kilograms. This system provides a convenient reference point for comparing different stars throughout the universe. The Russell-Voigt theorem establishes that if we know a star's mass and chemical composition, we can use fundamental physics to determine all its other characteristics, including how these properties change over time. This principle demonstrates why mass classification remains so crucial for understanding stellar behavior and evolution. The mass distribution of stars in our galaxy follows a well-established pattern known as the initial mass function, which describes the relative numbers of stars born at different masses. This distribution heavily favors lower mass stars, meaning that the universe contains far more small stars than massive ones. The relationship between stellar mass and other properties follows predictable mathematical relationships, such as the mass-luminosity relationship, where more massive stars shine much more brightly than their smaller counterparts, but also consume their fuel much more rapidly. Before examining true stars, it's essential to understand brown dwarfs, often called failed stars because they represent the transition zone between planets and genuine stars. Brown dwarfs occupy the mass range from approximately 13 to 75 Jupiter masses, which equals roughly 0.012 to 0.072 solar masses. These objects possess insufficient mass to sustain stable hydrogen fusion in their cores, the hallmark of true stellar behavior. However, they do have enough mass to trigger deuterium burning, a less efficient nuclear reaction that occurs at lower temperatures and pressures than hydrogen fusion. The minimum mass required for deuterium burning, known as the deuterium burning minimum mass, represents the lower boundary for brown dwarf classification. Objects below this threshold are considered planets or planetary mass objects. At the upper end of the brown dwarf range lies a hydrogen-burning minimum mass, above which object can sustain the nuclear reactions that define true stars. This boundary occurs at approximately 0.08 solar masses, marking the transition from brown dwarfs to the smallest true stars. Brown dwarfs exhibit surface temperatures ranging from 250 to 3000 Kelvin, making them much cooler than even the coolest true stars. They gradually cool throughout their lifetimes as they radiate away their internal heat, never achieving the stable energy generation that characterizes main sequence stars. Despite their relatively low masses, most brown dwarfs maintain roughly the same radius as Jupiter due to the competing effects of gravitational compression and degeneracy pressure. This unusual property means that brown dwarfs can be significantly more massive than Jupiter while occupying similar volumes. Low-mass stars represent the most numerous stellar population in our galaxy, comprising approximately 70% of all stars. These stars span the mass range from the hydrogen-burning minimum mass of about 0.08 solar masses up to approximately 2.2 solar masses, though the exact upper boundary varies depending on stellar composition. The most common type of low-mass star is a red dwarf, also known as an M-dwarf, which dominates the stellar census despite being too faint to see with the naked eye from Earth. Red dwarfs occupy the mass range from 0.08 to 0.6 solar masses and exhibit surface temperatures between 2000 and 3900 Kelvin. Their relatively cool surfaces give them their characteristic red color, and they represent the smallest type of hydrogen-burning star. Despite their diminutive size, red dwarfs possess remarkable longevity due to their efficient fuel consumption. Stars with masses below 0.35 solar masses are fully convective, meaning that material constantly circulates throughout their interiors. This convective mixing prevents helium buildup in the stellar core, allowing these stars to burn a much larger fraction of their hydrogen fuel compared to more massive stars. The main sequence lifetime of low-mass stars increases dramatically as mass decreases, while our Sun, with one solar mass, will spend approximately 10 billion years burning hydrogen in its core. A red dwarf with 0.2 solar masses could potentially shine for 560 billion years. The smallest red dwarfs may have lifetimes exceeding 10 trillion years, far longer than the current age of the universe. This extraordinary longevity means that every red dwarf star ever born is still shining today, since none has had sufficient time to exhaust its nuclear fuel. The nuclear fusion processes in low-mass stars proceed through the Proton-Proton chain reaction, where hydrogen nuclei combine to form helium while releasing energy in the form of photons and neutrinos. The lower core temperatures and pressures in these stars result in relatively slow fusion rates, which explains both their dim luminosities and extended lifetimes. As these stars age, they gradually increase in luminosity and temperature while remaining on the main sequence, a phase that constitutes roughly 90% of their total lifespan. When low-mass stars eventually exhaust their core hydrogen, they undergo a different evolutionary sequence than more massive stars. Stars below approximately 0.5 solar masses will directly evolve into white dwarf stars without passing through the asymptotic giant branch phase. Stars between 0.5 and 2.2 solar masses will experience helium fusion in their cores, developing into red giant stars before eventually forming white dwarf remnants surrounded by planetary nebulae. The boundary between different evolutionary paths within the low-mass category reflects the minimum core temperature and pressure requirements for helium fusion. Intermediate mass stars occupy the mass range from approximately 2.2 to 8 to 10 solar masses, representing a crucial transition zone between low-mass and high-mass stellar evolution. These stars are massive enough to ignite helium fusion in their cores, but not quite massive enough to progress through the complete sequence of nuclear burning stages that characterizes the most massive stars. The exact boundaries of this category depend somewhat on stellar composition, with metal-rich stars requiring slightly different mass thresholds than metal-poor stars. Stars in this mass range spend their main sequence lifetimes burning hydrogen through both the Proton-Proton chain and the CNO cycle, depending on their core temperatures. The CNO cycle becomes increasingly important as stellar mass increases, providing a more efficient pathway for hydrogen fusion at higher temperatures. This enhanced fusion efficiency means that intermediate mass stars shine much more brightly than their low-mass counterparts, but also consume their fuel more rapidly. The main sequence lifetimes of intermediate mass stars range from approximately 100 million years for an 8 solar mass star to several billion years for a 3 solar mass star. These lifetimes follow an inverse relationship with mass, where doubling the stellar mass reduces a lifetime by roughly a factor of 10. This relationship reflects the competing effects of increased fuel supply and dramatically enhanced fuel consumption rates in more massive stars. When intermediate mass stars exhaust their core hydrogen, they evolve off the main sequence and undergo helium burning in their cores. This process, known as the triple alpha process, converts 3 helium nuclei into carbon, releasing energy and enabling the star to continue shining. The core conditions in these stars are hot and dense enough to ignite helium fusion without the explosive helium flash that occurs in lower mass stars. During this phase, intermediate mass stars develop to generate carbon-oxygen cores surrounded by helium and hydrogen burning shells. Some intermediate mass stars may proceed to carbon burning if they are near the upper end of this mass range, though most will not achieve the core conditions necessary for this advanced nuclear process. The minimum stellar mass required for carbon burning is approximately 4 solar masses, though this threshold can vary based on stellar composition and other factors. Stars that undergo carbon burning can produce elements up to neon and magnesium before their nuclear fires are extinguished. The final fate of intermediate mass stars depends on their initial mass and the amount of mass lost during their evolution. Most intermediate mass stars will eventually expel their outer layers through stellar winds and pulsations, forming planetary nebulae while leaving behind white dwarf remnants. However, stars at the upper end of this range, particularly those retaining masses above the Chandrasekhar limit of approximately 1.4 solar masses, may undergo more dramatic endings. These stars might experience carbon deflagration or detonation events, potentially leading to Type Ia supernovae or other explosive phenomena. This video is getting long, so I'll stop here. Expect the rest of this in the next video. You can see more valuable videos by clicking on the card shown here. If you want to see our next video as soon as it comes out, subscribe to our YouTube channel and click the bell icon. Thank you very much for watching the video so far.